Some of you worry a lot about your hair's porosity, and there's a fair amount of conversation about low porosity and high porosity and fixes for both. But did you know that low porosity is actually a natural characteristic of healthy virgin hair? On hair that has just emerged from the scalp, you should expect to see droplets of water sit on the outside of the strands for a long while before sinking in. And in the case that that doesn't happen, it's normally a sign of wear and tear or some sort of scalp pathology. But why is this the case? This is due to the naturally water-resistant structure of your hair, and it's not as simple as you may think. Today's video explores water and cuticle science in delicious detail, so you can appreciate your hair's sophisticated structure the next time you wet it. Alright, so firstly, let's talk about water. It's literally everywhere, and its presence is responsible for life on Earth. In one molecule of water, 2 hydrogen atoms share electrons with 1 oxygen atom. You may remember electrons from your secondary school chemistry class. It just so happens that, like some humans, some atoms are a bit more selfish than other atoms. And in the case of hydrogen and oxygen loves electrons a bit more than hydrogen. So in a molecule of water, oxygen draws the electrons it's supposed to be sharing with hydrogen towards itself. Since electrons have a negative charge, this gives oxygen a partially negative charge and each hydrogen a partially positive charge. Technically known as a dipole, so where there is this imbalance between the sharing of electrons in a molecule, this is responsible for water's incredible properties. Specifically, this means that water forms relatively strong bonds with other molecules of itself. So a partially negative oxygen from one molecule will be attracted to the partially positive hydrogens from a neighbouring molecule of water. And this property is called water's cohesion. When you try to wet something, there's now a competition between the attraction of the water molecules to each other and their attraction to the surface, and this can be expressed using the contact angle. When the cohesive forces between water molecules are higher than their attraction to the surface, the water forms a ball on the surface and the contact angle is high. On the other hand, when water is attracted to the surface, it spreads more and the contact angle is lower. The time it takes for water to be absorbed by hair is used by researchers as a direct measurement of how damaged it is. This diagram shows that at 1 second, the droplet just sits on the strand, but as time progresses, the contact angle decreases and the hair eventually soaks up the water. But if hair is so resistant to it, how does water get in at all? Let's nerd out on some hair science. Your hair has 3 main layers with unique properties. These are the outermost cuticle with flattened cells that overlap, kind of looking like a stack of cups or tiles on a roof, the cortex, which makes up the bulk of the hair strand, and the medulla, which is the centermost portion of your hair, only present in very thick hairs and mostly filled with air. We will look at water's pathway into the hair with a focus on the cuticle and a little bit on the cortex, but more on the cuticle. Before we zoom into these structures in more detail, let's first consider keratin. What is keratin exactly? Well, keratin is a resilient protein material found in nails, skin, horns, and feathers, and its main function is to protect animals from their surroundings and also make them look cute. Proteins are made of building blocks called amino acids, and different amino acids have different structures and properties. And these different structures and properties influence the way amino acids join together to form proteins, and that influences what we perceive when we look at proteins. One of the most important characteristics of keratin is its abundance in the amino acid cysteine. See that yellow ball on the side? That's sulfur, and that's what makes cysteine unique. This sulfur allows cysteine to form relatively strong bonds with other cysteines in keratin, and these are called disulphide bonds. Di meaning 2 and sulfide coming from sulfur. Why is this at all relevant? Well, it just so happens that the more disulphide bonds in a protein, the more resistant that protein is to water. And keratin as a protein, with a lot of disulphide bonds. I see you're enjoying the hair science in this video, but how much do you know about growing long, healthy hair for the first time? Take my quiz to find out your healthy hair IQ. Click on the link in the description box to put your knowledge to the test. We mentioned that keratin has a lot of disulphide bonds, but there's actually variation within hair. There are some regions of your hair that have more disulphide cross-links than others. And as you can imagine, the regions with more cross-linking are also more resistant to water than the regions with less cross-linking. Let's zoom into the structure of hair to get a closer look. This is actually quite logical. The outside of your hair behaves kind of like a shield that protects the inner portions of your hair from the environment. Now, bearing this in mind, do you expect the outside of your hair to have more cross-linking or less cross-linking? Put your guess below and no cheating. Pause the video. Okay, drum roll please. The outermost portion of your hair, known as the cuticle, is highly cross-linked and is the most resistant to water. As a general rule, the further into your hair you go, the less cross-linked it is and the more permeable it is to water. If we zoom into the cuticle even more, we'll see that it's comprised of multiple sublayers. Don't you love biology? The more you zoom in, the more complex it gets. If we look at this simplified diagram of the main portions of a cuticle scale, we can see that it's divided into three main layers: the epicuticle, the exocuticle, and the endocuticle. The outermost layer of the cuticle is called the F layer, and it's a lipid. What does that mean? It means that it's hydrophobic, so it repels water, and it's something like a fat or an oil. Why isn't water attracted to the surface of your hair? Well, water does this incredible thing where, remember, it's dipole, so it's partially positive and negative charges. Well, because of that, it's able to form what are called hydration shells around other species that have a charge. Let's take table salt, for example, sodium chloride. You can dissolve that in water, and that's because it also forms positive and negative charges in the water, and then the water is attracted to those charges and forms little shells around the sodium, which is positively charged, and the chloride, which is negatively charged. Since fatty substances don't have a charge, water isn't attracted to them. And this is why water droplets sit on top of healthy hair, which has an intact fatty layer. Below the F layer is the epicuticle, which is a really tough layer, and that's because of its, you guessed it, very high cross-linking. It has a lot of disulphide bonds. The exocuticle, just like the epicuticle, is also highly cross-linked, and so it's also resistant to water. But then there's the endocuticle, which doesn't have much cross-linking at all and swells a lot when you wet your hair. At this point, you might be wondering, if hair is so resistant to water, how does water get in at all? Well, while the F layer, epicuticle, and exocuticle are resistant to water, as we've seen, there are other regions of the hair, such as the endocuticle, which we've just looked at, and the cortex, which is delightfully complex as well, which do absorb water. Ultimately, the absorption of water boils down to an interplay between the attractive forces and the repulsive forces. In general, the more intact the cuticle, the less readily your hair will absorb water. And this is why you will probably notice that your roots do not absorb water as readily as your ends. Through damage from the sun, wind, friction, braiding, combing, colouring, and heat, your hair loses its protective F layer, epicuticle, and exocuticle. This exposes the less water-resistant protein portions of your hair, making your hair less water-resistant altogether. The more damaged your hair, the less water resistant it is. If you liked this video and you enjoy nerding out to hair science, click on the link in the description to put your knowledge to the test. You'll also like these videos here, which also delve into the science of hair in delicious detail, of course. My name is Asha. I'm a certified trichologist in training, and I help new and overwhelmed naturals grow long, healthy hair for the first time.